a flow rate of 1,150 kilogram per hour. Superheated steam at 300 degrees C and 1 atm is needed. That means when it says it's needed, you know that is going to be your output stream. Okay? To produce that stream, 300 degrees C and 1 atm, you need to have that stream which is having a flow rate of 1,150, mix it with another superheated steam which is available at 400 degrees C and 1 atm. Your mixing is going to be done adiabatically. You need to the question asks for the amount of superheated steam that is going to be produced from the mixer and the volumetric flow rate of your second stream, which is at 700 degrees C. So I'm going to show you guys my iPad so that we can start solving that problem. Okay. Again, this question is a bit it's not straightforward, but it looks the same as the previous example. Actually, it's a mixer. Okay? It's not a boiler. The previous example was a boiler, but this one is a mixer. Let's look at the question. You have state saturated steam. Oh, if I could, okay, let's use a marker. Saturated steam, 1 atm, flow rate 1,150. You're going to produce superheated steam at 300, 1 atm. That's superheated steam. Is the one that is the outlet stream. The other stream is superheated steam at 400 degrees C and 1 atm. So you have 3 streams over here. The outlet is the superheated steam at 300. The 2 inlet stream is the saturated steam and the superheated steam. So let's draw our block diagram. But before that, let me get rid of... Okay, first, what you need to do, guys? If you don't know what is going on, you have to draw the diagram. Okay, sorry. What was the what did you just mention? What's the first thing?
Basis.
Basis. Okay, what's the basis? What's the basis?
We can choose either 1,150 kg per hour or the other.
Per hour.
Okay, thank you, Gan and Sulaiman. Okay. Okay. So that's your basis of what? Of saturated steam. So write down your stream coming in. And now, what you have to do next is draw your block diagram. And coming in is that 1,150 kilogram per hour of saturated steam. Okay. And you have another stream coming in, which is that of your superheated steam. Your superheated steam, you don't know the mass flow rate, so let's give it flow rate of M2 because this is M1. Okay, that is superheated steam. Oh, hold on, I need to erase that because I need to write down the unit. Let's label it properly. Should be kilogram per hour of superheated steam. Okay, and what's the temperature given? The temperature is 400 degrees C, and the pressure is 1 bar. Oh, sorry, 1 atm. Okay, another thing, your saturated steam is at 1 atm. Okay, and the stream coming out is the desired stream, which is superheated steam. Again, you don't have that value, super kilogram per hour. You need to write down the kilogram per hour. Hold on. Superheated steam. Yeah, superheated steam. And what is the temperature? 300 degrees C and 1 atm. Yeah, that's the information that is available. Yeah, so next, what's the next step?
Reference state.
What again? Sorry.
Reference state.
Reference state. Okay, reference state. Before you do anything else, you need to have a reference state. So what's reference state are you going to use? What reference state are you going to use?
0.00611 bar and 0.01 degrees.
0.00611 bar. Your temperature 0.01 degrees C and
Liquid.
liquid water. Okay. Okay, that's your reference state. Okay, we have already, you know you're going to use the steam table because it's mentioned saturated steam, superheated steam. So obviously your reference state must be the same as that of your steam table. Steam table. Okay, thank you, Ibrahim. So next, what to do?
Find in M1, H1, H2, H3.
Okay.
Mass balance first.
Mass balance first. Okay, let's look at our stream. We have M1 plus M2, the same as the previous example, equals to
Yes.
M3. Okay, so M1 equals to M3. M1 plus M2 equals to M3. Okay, M1 is given 1150, but unfortunately you have two unknowns, but only one equation, you cannot solve it.
Mhm.
Okay, so what's next?
Yeah.
What's next? What's next?
Energy balance.
Energy balance. Okay, energy balance. What kind of system are you looking at?
Open.
Open system. Okay. So now it's mentioned, there's one information that I haven't listed down. What is it? From the question, there's one information that I did not listed down. What is it?
Adiabatic, doctor?
Adiabatic. Yes. Q is equals to 0. It's adiabatic. Yeah. That information should be listed down also. Okay, now let's write our energy balance. Our energy balance is an open system. So we have the enthalpy change. We have the kinetic change. Ouch. That's kinetic change. And the potential energy change. What happened? My pen is not, I'm not writing properly. Okay, equals to change in heat plus shaft work. Okay. You know that there's no change in potential because there's no mention at all about is there a differences of inclination or height. There's no mention at all about the size of the diameter of the pipes. So you know that's going to be no kinetic energy. Okay, so what else? There's no mention at all about pump or turbine or anything for turning. So there's no moving parts. So you only have Q is equals to, sorry,
No, no.
no Q, is it?
Yes,
Yes.
adiabatic.
Yes, adiabatic. So what happened now?
Del H equal to 0.
Okay, everything is equal to 0. Okay, so your change in enthalpy is equal to 0. Okay, so again, the change on enthalpy, if it's an open system, out minus in, you have your mass flow rate times by the specific enthalpy. Okay, mass flow rate, specific enthalpy. Okay, so you can do the steam table. If you sorry, you can tabulate it using the table if you want, just like what we did just now. Or you can just write it, the enthalpy that you get from the steam table on the block diagram. It's up to you. It's up to you. You want to have it in a table form, you can do that. Let's do it in table form so that we can see how it look like. Again, I'm going to simplify the whole thing need to be, let's see, that's in, out. Not sure whether I'm going to get it. Okay. This is in, this is water. No, sorry. There's no water, there's steam. Saturated steam. Superheated. I'm not going to write the whole thing. Steam. Okay. Superheated steam. This is in. The unit is in kilogram per hour. And this is my enthalpy in. Again, the steam table, kilojoules per kilogram. Okay, mass in is going to be kilogram per hour. And enthalpy in. Out, sorry, that's out. Supposed to be out, yeah. Kilojoules per kilogram. Let me erase that. Let me try to see whether, oh, sorry. I want to erase. That should be out. Okay. That should be out. Okay. So what do we have? The stream coming in for the saturated steam is 100, and let's look at our block diagram. Yeah, we have 1,150. Yeah. Coming in.
Doctor,
Yes.
shouldn't we have two inlets and one outlet on the table?
So outlet, yeah. We forgot about this. The steam, superheated steam, isn't it?
Yes.
There's another one. Okay. Okay, there's no inlet here. There's no outlet here. Okay. We got just like the same as the previous example. This is exactly like the same as the previous example.
Yes.
Okay, so thank you very much. So, oh, is that Aiman? Or is it Omar? Oh, it's Ibrahim. I cannot recognize your voices. Thank you, Ibrahim. Okay, that's coming in is M. Oops. Let's see. What's it? Is it M2? M2 and M3. Okay. This is M2. This is M3. Okay. Putting in the values of your enthalpy. You haven't have the values yet. So let's look at our steam table. I'm going to show you guys the, I'm going to stop this sharing this. I'm going to show the PowerPoint so that we have the steam table there. Okay. Where's the PowerPoint? Okay, here. Okay. What is the value that we have? We have saturated steam at 1 atm. This is 1 bar. 1 bar is approximately 1 atm, approximately. Okay. So if you look at this, let me try to scribble something here. Yeah. That's one. Oh, that's oh dear. Yeah, that's one. That's the value. Yeah, that's saturated steam, or is that the value? Which one? Which one is saturated steam?
2,675.
Yeah, that's it. 2,675.4. That is one ATM, approximately 1 bar, 1 ATM. Okay, so that's the value, 2,675.4. The one inside your textbook, if I show this, hold on, let me show the block diagram. Inside your textbook is 2,676. Over here is 2,675.4. Why is there the differences in value? Because we are assuming 1 ATM is approximately equal to, is it 1 bar? Is it 1 ATM? 1 ATM, isn't it? Yeah, but the table is based on bar. So that's the reason why there's a difference. Okay?
Doctor,
Yes.
it's referring to table B7, superheated steam. The state of the M1 is saturated. So,
Yes.
so
It is saturated.
why do we take from superheated steam table instead of the B6 table, saturated steam table?
Instead of B6.
Yes.
Okay, let's unshare this. I show you guys the steam table so that we know what B6 is all about. Okay, where is my preview? Okay. So this is B, where is B6? That is A, where is B6? Oops. Where is B6? Oh dear. This is all A. Sorry, this is Dinkoplis. I'm looking at the wrong table. Sorry, guys. This is Dinkoplis. This is a different textbook. Okay. I need to unshare this. Oh, I'm sorry about that. That's a wrong That's a wrong textbook. Let's see. I have here over here a thermodynamic textbook. Okay. Can you see? What's your view, guys? Are you looking at the thermodynamic textbook?
Yes.
Oh.
Yes.
Yes.
Okay. 1 atm is approximately how many megapascal?
Megapascal.
Megapascal.
Maybe 0.1.
Okay, hold on. Let's see. Let's look at the steam table. Okay. Saturated. 101, isn't it? 1 kilopascal. Kilopascal. 1 atm.
Yeah, 101.
101.325, right?
Yes.
Okay, so now if you look at my cursor, I'm going longitudinally to the enthalpy of saturated steam, saturated vapor. Okay, that's the value. If I can share, if I can show the scribble. Okay, this is the 1 atm. So that's the value at, if I can use whether I can, where is, okay, that's it, saturated vapor, which is saturated steam. So this is 1 atm, this is 1 atm. Yeah. So that's 2675.6, approximately 2676. I don't have the textbook, the appendix of the textbook, but the question just now, you asked why am I not using the appendix B6, is it?
Yes.
Okay, let me look at my appendix B6 then. I need to know what appendix B6 is all about. B4, B5, B6. Okay, B6 is about pressure and bar, property of saturated steam. Yes, you can use it. What's now? Let's look at, sorry? Sorry, what did you say?
I mislook.
Arif,
I
you
mislook
mislook.
I mislook the numbers.
Okay, 1 atm is there. Okay, if you look at B6, appendix B6 on page, I don't know what is your page, but I'm looking at the third edition. It's page 645. The enthalpy of saturated steam is 2676. Exactly.
Oh, it's the same. Okay.
Yeah, it's 2676. 1.01325, 1 atm, bracket, 1 atm, appendix B6. The enthalpy for saturated steam is 2676. Exactly. Yeah. For if you're using this thermodynamic data from thermodynamic textbook, it's 2675.6. You just round it off to 2676, no problem. Okay, next. The other part of the question states that you have superheated steam. So let's look at superheated steam. Since we are looking at this steam table, the pressure is 1 atm. The pressure is 1 atm, and you have 300 degrees C for the outlet. 300 degrees C for the outlet. So where is 1 atm at 300 degrees C? 1 atm is what? 1 atm is what, guys? How many megapascal?
0.1.
0.1, isn't it? 0.1. 0.1. Where is 0.1? That's 0.1. Okay? 0.1. How do you know is this that value? That is 0.1.
Upright now.
How do you know that is 1 atm?
0.1 megapascal.
Because when we convert it to what do you call it, the pressure, when we convert it, it's from a megapascal to, you will get 0.1.
Okay, thank you. Okay, so now, thank you very much. So now you're looking at the temperature of what? Just now the question said that the outlet temperature is 300, isn't it? So if you drag that, where is your enthalpy? H is your enthalpy. The symbol is H. That is your enthalpy. Okay. So the intersection is 3074.5. if you're looking at this thermodynamic table. If you're looking at your textbook, what appendix are you supposed to be looking at? Appendix what? B what? Should be B7?
Table B7.
Yeah, table B7. And the pressure, the 1 bar is approximately 1 atm. But you need to look at a temperature of 300. And if you look at that, the value is what? Losing at B7. What is the value? Have a look at your textbook. 300 degrees C, 3074. There's a slight difference here. The one that I'm showing you guys right now, 3074.5. But the one from appendix B7, 3074. There's a slight difference. Okay. The next, for the other stream that is coming in, it was at 400 degrees C at 1 atm also. So same pressure, but now it's a different temperature. So I'm going to use a different color. Let's use purple. So now we have this at 400. Let's drag it up higher. Okay. So what's the enthalpy? If you look at 400 degrees C, the enthalpy is, what is it? 3278.6, isn't it?
Yes.
Yes. So if you look at your appendix B7 at 400, same pressure, 400, the enthalpy is 3278. Just slight difference.
Exactly.
Yeah, exactly. 3278, exactly. Thank you, Ibrahim. So just whichever table you want to use. Since you're using the textbook, maybe we stick with the textbook. But I'm showing you guys this appendix because that's the appendix that I have. I need to get the appendix of the textbook. Okay, so let's jot down the value that we have in our solution. Let's unshare this. So far, any question on how to get these values from the steam table, guys?
No, no, no.
No, good. Okay, let's go back to my iPad. Okay, guys, give me the values. Nobody already left. Okay, you use the textbook, the values from the textbook. 2676, remember? That's from the textbook. And the other superheated steam at a temperature of 400 just now, 3278. We got this from the appendix of your textbook. And the other value for the enthalpy is 3074. This is from the textbook, the appendix from the textbook. If you are using the thermodynamic textbook, then the value will be slightly different. Okay, so that's done for that part. Next, we need to put it inside that equation for the change in enthalpy. So if we do that, let's continue with this since everything is there. So Q, sorry, delta H is equals to, oh, that's not, I don't have enough space. Okay, I want, hold on, and I'm not going to do it there. I'm not getting anything here. I'm going to use it in another page because I don't have enough space here. Okay, next page. Okay, so delta H equals to, wow, this is too big. The ink is too big. Yeah, it's okay. Change out mass. I'm repeating this equation, so you don't have to write this because it is already written. You already got it written down. I'm just repeating myself. Okay, so out. The value of out is M3 times by 3074. Yeah. So M3, 3074 minus your bracket because you've got two streams coming in. So let's look at the stream coming in. 1150 times 2676. Yeah, I'm going to write it 1150 times by 2676 plus the other stream, which is M2 times by the corresponding enthalpy 3278. Okay, we're not going to write down the unit, but we will write down the unit later on. So what's the answer? We don't know. It's equals to 0, isn't it? Because this is
Yes.
equal to 0. Okay. So this is one another. Is it this? Let's see. Your enthalpy, the unit is kilojoules per kilogram. Your mass is kilogram per hour. Yeah. So if you cancel that, your unit will be kilojoules per hour. That's the unit. So let's look at our material balance earlier that we have done. Material balance, where is our material balance? This is our material balance. Okay. Our material balance is 1,100. That's our material balance. That's our material balance. We need to solve it together. Let's put that material balance together with our energy balance. So 115 plus M2 goes to M3. So M3, where is M3? This is M3. So you need to substitute M3 inside the equation. So 1150 plus M2 multiplied with 3074 minus the whole thing over here. Let me use a different marker. Okay. The whole thing over here. Okay, the whole thing there. Okay. You substitute your M3. This is M3 inside here. And then solve for what is left. The only thing that is left is M2, isn't it?
Yes.
So did I make a mistake?
Yes.
Guys, M3. Is it M2 or is it M3? It should
M2.
be M2, isn't it? Okay,
Yes.
everything is there in terms of M2. So solve for M2. So what is the answer once you have solved for M2?
I got 2243.6.
M2, okay, let's change this to black. Okay. M2, you get, sorry, can you repeat that again, please?
2243.
Sorry, again?
43.
0.3.
2243.
343.6.
4.6.
Thank you. Aiman, thank you. Is it the same as the solution in the textbook? 2240. The textbook gives a value of 2240. Okay. 2240. There's a slight difference there. Okay. How about M3? You substitute that value of M2 inside this equation. Is equals to 2243.6. Once you substitute that, what is M3 then? What's the answer for M3?
3393.6.
3393.6 kilogram per hour. Yeah, so that's slight different from the textbook. The textbook is 3390 kilogram per hour. So that's your final answer. And what else is asked in this problem? You need to find the volumetric flow rate of the 400 degrees C superheated steam. Which stream is that? This flow rate. You need to get this flow rate of 2. You need to get that flow rate. Yeah, you need to get the stream, the superheated steam, the flow rate of it, volumetric flow rate in terms of meter cubic per hour. Okay, how to go about that? Let's
Find the specific volume from the table and divide it by the mass.
Okay, find the specific volume. Let's see. Your volume. Sorry, let me write that down. You need to find this. That the answer is in meter cubic per hour. You need to get that. You are given the, this is meter cubic. Meter cubic means that you're looking at volume. You have your value that you have for this, the, which one was it? M2 is now, you have 2243.6 kilogram per hour. You need to cancel the kilogram. You need to have a meter cubic there. You need to cancel the kilogram so that you have meter cubic there. So it becomes meter cubic per hour. So what is that value there. Yeah.
Is it like just
3.11, Doctor.
Sorry,
3.11.
3.11. How did you get that?
From the superheated steam.
Okay, from the superheated steam. Okay, I will just write that there. So that after this we look at our table. Yeah. So
Yes,
let's,
true.
sorry,
So 3.7. From 3.11.
3.11 is it?
Yeah.
Okay. 3.11. 3.11. Let's unshare this. Let's look at our PowerPoint. Our PowerPoint, I have the steam table there. It's at B7 with the temperature of 1 atm. Let me show you guys let me scribble something. One atm. That's 1 atm. The volumetric flow rate, sorry, that's the value, 3.11. The
Doctor,
unit is
I
meter
think
cube.
that's in bar, right? If I'm not mistaken.
Yeah, 1 bar is approximately 1 atm, approximately. We are just giving it an approximate. There's a slight change. There's a slight, very, very small change, but since it's approximately close, we can still use 1 bar is approximately 1 atm.
All right, thank you.
Yeah, thank you, Sulaiman. All right, so just now when we get the enthalpy, that's the enthalpy at 400. And when we're looking at 300, this is the enthalpy at 300 at 1 bar. And when we're looking at 1 atm, saturated at 1 atm, the steam is supposed to be, this is the saturated value. Yeah. But over here, the author wrote 2676. This is just round off. 3074, 3074 at 300. At 400, 3278. That's the value from table B7. Okay, so now let's go back to our solution. We're going to stop, we're going to unshare this and go back to our iPad, to my iPad. Right. So the final answer, volumetric flow rate, will be what, guys? In meter cubic per hour. Give me a value, please. Anybody? Sorry?
6977
Point
596.
59. So just round it off to 6 then. Okay, 6977.6. Anybody get the same answer as Omar?
Yes.
Yes,
Good.
I'm answer.
Okay, so that's the final answer. Your volumetric flow rate for the superheated steam that is coming in at 400 degrees C. Right. So far, how's any question? Any question that you need to ask? Anything? We have solved this problem simultaneously because there's two unknown. You cannot solve for the material balance because you have only one equation but two unknown. So you need the heat energy balance, the energy balance to solve it. Remember, you have two inlets. You can choose, you got only one flow rate, so you use that as your basis. Even though you got two inlets, you have only one flow rate given, so that is your basis. Be very specific when you write the basis. State down that it is saturated steam in this case. State down if it's water, write down as liquid water if it's water. That be very specific. Any questions? Every time you have steam, every time you have water, you know you're going to use the steam table. Anytime you have superheated steam, you know you're going to use the steam table. So your reference state must be the same as the steam table. Right. Any questions, guys? This
Yes,
is yeah. I wrote here superheated steam. Both of them superheated steam because they have different temperature, so it's not going to be the same superheated steam. And in fact, one of them is coming in, the other one is coming out. Yeah. Different temperature, so it's different column.
Doctor.
Yes.
Will the tables be provided in the exam? The test?
You have to draw the table. I mean, you have to tabulate yourself.
I mean, the saturated steam table.
Oh, your exam is going to be open textbook, open internet. You can access anything you want because it's online. But
Okay.
normally the norm was just like how you did it last time. I'm not sure whether you have the chance to have a proper test one last time. The norm is that you have the textbook as your reference. You're only allowed the textbook as your reference. So I would suggest if your STEAM table, you stick with the textbook STEAM table. But then, if you use the thermodynamic STEAM table, it might be the big slight differences then.
But doctor, I can't find steam tables with the specific needs, like steam table that specify with bar, PAR, or ATM.
Okay. Just now when we were looking at appendix B7, B6. If you look at appendix B6, remember just now they specified that 1 bar, not 1 bar, the temperature. The temperature was given, bracket 1 ATM. Is it 1 bar or is it 1 ATM? Bracket, let me have a look at my appendix. B6.
Bar.
Bar.
Yes.
Hold on, B6. Okay. But look, the top, the labeling, the top is pressure, bracket bar, isn't it?
Yes.
Okay, let's look at the second page. The second page, bracket 1 ATM. At the very bottom. You managed to find that?
No, doctor.
The second page. The second page. Appendix B6 at the very bottom.
I only have bar and T in Celsius.
I see. The bar is 1.01325. Did you manage to find that? Appendix B6. The bar is 1.01325.
I have 1.1.
1.1.
Yes, I have 1.01325.
Okay. Above it is 1 bar.
Yes.
Yes, so that means both values are given there. You have the 1 bar and 1.01325. 1.01325 is equivalent to 1 ATM. So you can see the differences in the values. The one above and the one below. One of it is for 1 ATM, the other one is for 1 bar. You can compare.
Okay, doctor.
Okay, good.
Thank you.
You're welcome, Ayman. Any other questions?
Doctor,
Yes.
for example, if the question gave us a pressure at 25 ATM, should I assume that 25 ATM equal to 25 bar, or should I convert it?
Okay. If you want to play safe, you convert it.
Sorry?
You convert it. You do the conversion.
Okay.
Okay. Because if you look at the values for 1 ATM and 1 bar, there's a small change different there. There's a difference. Definitely there's a difference. There's a small differences. So if you want to use just the exactly 1 ATM is equal to 1 bar, then your answer will have a slight differences. Yeah.
Okay, thank you, Doctor.
Okay, you're welcome. Any other questions? Because the differences is not that much, The 1 ATM is equal to 1.013 bar. So in terms of engineering wise, that is less than 5% difference. Anything else? Besides the steam table? Anything else? Guys? Okay, if there's no question on this example, let's go back to our PowerPoint. Okay. I'm going to stop sharing this. Let's share our PowerPoint. Okay, this is the example that we just covered just now. Okay, so let's look at. Okay, that's the enthalpy. We have done that. Now, this is one problem from the back of the chapter, but this is from appendix, this is from the third edition. You have 300 and, what's the flow rate? The flow rate is 200 kilogram per minute of steam coming in at a temperature of 350. Where is my cursor? Okay, 350, 40 bar, having flowing inside a diameter of 7.5 centimeter, and the outlet is going out at 75 degrees C, 5 bar, and 5 centimeter. The question is, how much energy is transferred to or from the turbine? Does this look familiar to you guys? Does this question, is it the same as the one that we have covered before?
Probably yes.
Yes, let's look. Let me show you guys. We did cover something like that. This one, I just, there. We covered something like this, similar to that problem. This is one example I already discussed with you guys. So by right, you should know how to solve that problem. Okay? You need to solve, in this case, there's a heat loss, but in that example, that problem just now, there's no mention of heat loss. So let me quickly go back to that problem. Okay. So, is there any problem with this? Do you think you can solve it? This is steam coming in. Do you know whether the state of the outlet, is it steam or is it liquid water?
I have to check.
Check the temperature. Okay. Now, use your steam table from the appendix. I'm going to ask you guys, you have your textbook with you. At 75 degrees C, what is the state at 5 bar? At 5 bar, 75 and 5 bar. Look at appendix B7. B7.
151.8.
Hold on.
151.8.
The temperature.
Yeah, then this is compressed liquid.
Hold on. I'm still looking at my table. Okay. 5 bar, the temperature is 151.8. Under the 5 bar, there's a bracket. Everybody managed to get that temperature? Look at appendix B7, please, from the your textbook.
Yes, doctor, 151.8.
Okay, 151.8 degrees C. That is the saturated temperature. So let me scribble. Desaturated. Very slow. Going somewhere. 151.8 degrees C. So that is the temperature saturated at 5 bar. But what is the temperature given now for this problem? For the outlet? 75, right? It's 75. 75 is less than T saturated. It's less than T saturated. So what state is that outlet?
Liquid.
Liquid. So this is going to be liquid water. Okay, this is going to be liquid water. Oops. It's going to be liquid water. It's not steam. So what value are you going to get from which condition are you going to, how are you going to get your specific enthalpy from the steam table?
Go to 75 degrees C and look at.
Okay, you should be looking at 75. When you're looking for the specific enthalpy, it should be at 75 degrees C, not at the 5 bar. Why? Why is your specific enthalpy at 75 and not at the 5 bar?
Because it's liquid, doctor.
Yeah, because it's liquid. Okay, it's liquid, so liquid is incompressible, so it is not affected by the pressure. So it's more affected by the temperature. So you should get your enthalpy at 75 degrees C, not at 5 bar. For this question, this is 350 degrees C and 40 bar. It's mentioned that it's steam. Okay, now look at your appendix. Do we have 40 bar? Yes, you have.
Yes, yes.
So what's the temperature? Oops.
250.3.
Okay, T saturated at that 40 bar. If I just write S there for saturated, the temperature is 250. 250.3 degrees C. Okay, so what's that temperature here? 350. That is greater than the saturated temperature. So what state is your steam coming in?
Superheat.
Superheated.
Sorry?
Superheated.
Superheated.
Superheated. Yes, you are looking at superheated. So it is superheated. Let me write superheated. So if it's superheated, you need to use the superheated steam table, and you need to use both the temperature and the pressure to get the value of your enthalpy. Okay, so now it's superheated steam. So whenever you look at a problem, you need to look at the saturated temperature based on the pressure. Then you compare the actual temperature with the saturated temperature. If it's greater than, for in this case, 350 is greater than the saturated temperature, you know it's superheated steam. Then you use the steam table, the superheated steam table. You use both values of the pressure and the temperature to get your enthalpy. But for the outlet here, you know it's liquid water, then you only be using the temperature to get the enthalpy. You don't need the pressure at all. Okay, guys?
Okay.
Okay. So what's the value of this superheated, what's the enthalpy? Since we are already looking at the steam table now, what value do you have at 350? I need to get
3095.
the cap.
Yes.
Okay, let's see. Muhammad Faisal, you're looking at 350 at 40 bar.
Yeah.
What's the value just now?
3095.
3095. Okay. 350 at 40 bar. 3095. Yeah. 3095. Okay. How about the value of this enthalpy here at 75 degrees C? Do you think do you have that temperature?
You need
75?
to interpolate.
No, you need to interpolate. Yes. You only have 74 and 70. Sorry, where is it? 75? Do you have exactly?
75.9 you have. Not exactly.
No,
Temperature.
there's 75 degrees
There
Celsius.
is it?
Yeah. I can see 75 degrees.
You can see 75. I'm looking at B5. We are looking at
No.
what?
I'm looking at B7.
B7.
Mm.
Okay, B7. I'm looking at B5. B5 is for okay, B7, 75. Where?
5 bar.
75 bar? No, we're not looking at 75 bar. It's degree C.
No, 5 bar at 75 degrees Celsius.
5 bar. No. You know why we're not using that?
Why?
Because we're not looking at 5 bar at 75? 314.3.
Yes, 314.3, yeah. Says here.
Okay. That's 314.3, 5 bar, 75. 314.3. Somebody is liquid water. That equals to 314.3. I'm not sure. Just now I said don't look at the superheated steam because it is liquid. But definitely it's liquid. It's below the line. Okay, that's now see whether you can solve it, whether you can get the same answer. Okay. Whether you can get the same answer.
No, doctor, it's not.
No, it's not. Why?
Yeah, you have to interpolate because the temperature is higher. This is liquid.
It is liquid. Okay. Just now I mentioned that because it's liquid, you don't really depend on pressure.
Yeah.
So if you use 75 degrees C, you look at appendix B5, isn't it?
Yes.
Yeah.
But
At
there's
75, you need to interpolate between 74 and 76.
Yeah, 72.7 and 75.9.
So you will get something between 318 and 309. Sorry, it will turn out maybe the same. It might turn out maybe the same. See whether you interpolate, whether it's the same or not. 309.8 and 318.2, whether you get 314.3. The enthalpy of water, liquid water, between 74 and 76 degrees C, if you interpolate. See whether you're going to get the same value, whether same 314.3, whether it's the same. Okay? And then after that, try to solve this problem. Okay, guys, I'm not going to wait for you guys to do it. I'm just telling you how you can do it. So next, let's look at this another problem. This is mixing chamber, just like the example that we did just now. Same thing. Okay? Same thing. The procedure is the same. The procedure is the same, but different set of questions. So this is problem 735. Okay, guys, you have the answer there. You can try to solve it, whether you can get the same answer. Okay? I'm not going to do it in class because we have already done an example that is exactly, that is not exactly the same, but the procedure is the same. It's a mixer. We have done that. So you should be able to know how to do this. Okay? Try to do it on your own and see whether you come up with the same answer. Okay, guys? Any questions? Any questions? It's already 3:52. Any questions? No questions?
No question.
Okay, for those who haven't slide in, using the barcode, I'm going to display this. Okay. You're going to have your first test on the 18th of November. We have one more topic that we need to cover. We need to cover mechanical energy balance. Mechanical energy balance will be asked in the test. It will be one of the questions. Two of the questions will be on what we have discussed so far. So we have, I think by next Sunday, we should be able to finish the whole of chapter 7. Okay? So by Monday, we should be starting chapter 8. I will give you your assignment by this week. You should be able to do the question based on what we have discussed so far. You might not be able to do the mechanical energy balance yet because we're going to cover that next week. Okay, guys? Anything you need to add up or anything you need to ask?
Doctor.
Yes. Omar?
The test will be only 3 questions, right?
Yes. 2 of the question will be something like, the one that we discussed in the example that we discussed, steam tables and all that. But the other problem will be in terms of mechanical energy balance. Mechanical energy balance is all about fluid mechanics. Have you taken fluid mechanics, you guys?
No, Doctor.
No.
No, okay. So it's about fluid mechanics. Mechanical energy balance is all about fluid coming in and out, having a pump or turbine, different elevation. So the equation will be different. You will be looking at an energy balance that has the equation is really different from the one that we have looked at before. Slight differences. You'll be looking at Bernoulli equation. Okay. You can look at the example if you want to go be ahead of the class. No problem. It's not that difficult to understand, but it's more like fluid mechanics. Since you guys haven't attended fluid mechanics, so it's something new to you guys. Since okay, it's 5 minutes too. Do you have any class after this?
No, Doctor.
No, okay. So try to solve the 2 example problems just now. P33 and P35. See whether you can get the answers. Okay.